What is quantization of energy? Quantization of energy means when an atom absorbs or emits energy, it absorbs like small packets of energy. It can absorb one packet of energy or two packets of energy or three packets of energy. Like that, atom absorb or emit an integer multiple of packets of energy. Atom cannot absorb any amount of energy, or atom cannot emit any amount of energy. When an atom absorb or emit energy, it does as small packets of energy. For example, if I take water from tap, means if I collect tap water, I can collect any amount of water, any quantity of water. If I want to take 1 liter water from the tap, I can take 1 liter water. If I want to take 2 liter water, I can take 2 liter water. If I want to take 1.5, it's possible. 1.5 liter possible, 1.7 liter possible, 1 liter 600 ml possible, 1 liter 550 possible. Means if we take water from the tap, we can collect any quantity of water from the tap. Means here the quantity means the amount of water is continuous, because you can take any quantity of water. Then instead, if we take like a bottle of water, means if there is a case of bottle of water like this is 500 ml, so I can take one bottle 500 ml. I can take two bottle, so 2 times 500 ml, now 1 liter. I can take 3 times 500 ml. So this is a packet, a bottle of water, and if the water is in the bottle, I can take as integer multiple of small packets of water, small bottle of water. So here the quantity of water is quantized when water is provided in small bottle. So you can take one bottle, you can take two bottle, you can take three bottle. So if it is given as bottle, can we take 600 ml? Not possible, right? You can take either 500 ml or 2 liter, or 1 liter, 1.5 liter, like that. Integer multiple of means one bottle, two bottle, three bottle, like that. Okay, so that is an example. So in the case of atom, what is the quantization of energy means? Atom emit or absorb energy, or when an atom emit or absorb energy, it absorb as small packets. So what is the value of one packet of energy? One packet of energy E equal to H times F. So what is E here? E is the energy of one photon. What is the meaning of photon? Photon is the one packet of energy of electromagnetic radiation. One packet is called photon. So this is energy of photon, we will say. Energy of photon. What is photon? Photon is one packet of electromagnetic radiation. And what is this H in this equation? H is the Planck's constant. Planck's constant. The value of Planck's constant is 6.626 times 10 to the power minus 34. What is F here? F is the frequency of the radiation or frequency of the vibration of the atom. So we will write F is the frequency. F is the frequency. So when an atom absorb or emit energy, it does it as small packets, emit small packets or absorb small packets of energy. Okay, then we will see this equation. What is H in this equation? H is equal to Planck's constant, that I can write E divided by F. What is E? E is the energy, and what is the SI unit for energy? SI unit of energy is joule, and what is the SI unit of frequency? hertz, right? SI unit of frequency is hertz. Hertz means second to the power minus 1. So if I take second to the power minus 1 to the numerator, it will be second, right? So what is the SI unit of Planck's constant? Joule second. SI unit of Planck's constant is joule second. So what is the value of Planck's constant? 6.62, 6 times 10 to the power minus 34 joule second. Okay. So when an atom absorb energy, how much energy it will absorb, or when an atom emit energy, how much energy it will emit? That is equal to energy absorbed or emitted by an atom, that is equal to N times HF. What is HF? HF is the energy of one packet. So if an atom emit one packet, its energy is, means how much energy it is emitted? It is emitted 1 times HF. So what is N? N is 1, 2, 3, 4, etc. means N is integer. When an atom absorb 2 packets of energy, how much energy the atom will get? The atom will get 2 times HF, like this. So what is the concept of quantization of energy? When an atom absorb or emit energy, it does it as like small packets. It can absorb 1 packet of energy, it can absorb 2 packets of energy, it can absorb 3 packets of energy, but it cannot absorb a half packet. It cannot absorb a fraction of energy. So we know the wave equation. What is wave equation of electromagnetic waves? Wave equation is C is equal to F lambda. What is C? C is the speed of the electromagnetic radiation, electromagnetic waves. C is the speed of electromagnetic waves. What is the value of the speed of electromagnetic waves? It is 3.0 times 10 to the power 8 meter per second. And F is the frequency, that you know, F is the frequency. What is lambda? Lambda is the wavelength. Lambda is wavelength. So this is the wave equation. You know that you have studied in grade 10, grade 11. C equal to F lambda. So from this equation we will write an equation for frequency. Frequency equal to what? Frequency equal to C by lambda. Rewrite this equation for frequency. So lambda will come to the denominator of the equation. So it will be C by lambda, right? So frequency F is equal to C by lambda. This one, frequency F is equal to C by lambda, we will take this equation to here. So we have this equation, energy equal to HF, energy of one quantum, one photon, one packet, that is equal to HF. So energy that is equal to, if frequency is not given, instead of frequency wavelength is given. So how will you calculate the energy? How will you calculate the energy of photon, energy of one packet, if wavelength is given instead of frequency? We know that frequency is C by lambda. So energy equal to Hc by lambda, energy equal to Hc by lambda. Okay. The next step, what is H? H is 6.626 times 10 to the power minus 34. What is C? C is 3 times 10 to the power 8 meter per second. So when we multiply this H and C, we will get like this: 1240 times 1.6 times 10 to the power minus 34. Sorry, 1.6 times 10 to the power minus 19 times 10 to the power minus 9. Okay, when we multiply, we will get something like this. Divide this lambda, I will write the lambda. Okay, so what is 1.6 times 10 to the power minus 19? 1.6 times 10 to the power minus 19 is charge of 1 electron. 10 to the power minus 9 is nanometer. 10 to the power minus 9 is, sorry, Meter will be here, okay. 10 to the power minus 9 is nano. So what we can do, we can write this equation like this. We will write 1240 EV nanometer divided by lambda. So what is this? This is the equation to calculate the energy of one packet in electron volt. So what is electron volt? Electron volt is a unit of energy. Okay. So what is this equation? 1240 EV nanometer divided by lambda. The equation to calculate energy in electron volt if the wavelength is given. Equation to calculate energy in electron volt when the wavelength is given. So you have three equations now. What are the three equations? E equal to HF, energy of one packet if frequency given. E equal to Hc by lambda, energy of one packet if wavelength is given in the question. Third equation, E equal to 1240 EV Nm divide by lambda. The equation to calculate energy in electron volt, equation to calculate energy of one packet in electron volt if wavelength is given in nanometer. Okay, so now we have three equations. Then what is electron volt? See, electron, proton, for these subatomic particles, they will have very small amount of energy, but we say energy in joule. Joule is like 1 joule is a very big amount, a large amount of energy compared to the energy of the electrons, protons, like that, very small subatomic particles. So we need a unit to represent the energy of, like, the very small energy of the subatomic particles. So we have this unit, electron volt. So electron volt is a unit of energy to represent the energy of the subatomic particles like electrons, protons, because joule is 1 joule, if you say, it is a very large amount of energy. Okay, so what is 1 electron volt? 1 electron volt is, for example, there is an electron. Here there is an electron. What is the charge of electron? 1.6 times 10 to the power minus 19 coulomb is the charge of electron. Okay, you are applying a positive potential here, positive potential. A negative potential means you are connecting a small battery or a cell here. So there is a battery, or yes, okay, negative and positive, right? Positive, negative, yeah, okay, correct, like this. So how much voltage you are applying? You are applying a potential difference of 1 volt. So what happens to this electron? Electron has negative charge, right? Electron has negative charge. So this electron will be attracted to the positive terminal of the battery. So the electron will be attracted to this side. When electron is attracted, it will move to that side. When it moves, it gets kinetic energy. When electron is accelerated, the electron gains kinetic energy. How much kinetic energy? How to calculate the energy gained by an electron? So energy of an electron, or energy of a charged particle, that is equal to charge multiplied the potential difference. And what is the charge of electron? Charge of electron is E, right? E into potential difference V. So energy gained by the electron, that is equal to EV. E times V. Okay, so energy equal to, what is E? E is equal to 1.6 times, means charge of the electron, okay, 10 to the power minus 19. How much potential difference you applied? You applied a potential difference of 1 volt. 1 volt, right? So I will write 1 volt, 1, okay, yeah, 1 volt. So how much is the energy? Energy is equal to 1.6 times 10 to the power minus 19 joule. So this is called 1 electron volt. Energy gained by an electron when you apply a potential difference of 1 volt. Okay, you keep the electron in a potential difference of 1 volt, so that electron gain a kinetic energy. That much energy is called 1 electron volt. So how much is 1 electron volt? 1 electron volt is equal to 1.6 times 10 to the power minus 19 joule. So this is 1 electron volt. Practice problems. Question number 1. What is a photon's energy if photon wavelength is 515 nanometer? So if the wavelength is given here in this question, wavelength is given. So if the wavelength is given, what is the equation to calculate the energy of the photon? Energy of photon, that is equal to 1240 electron volt nanometer divided by wavelength. So this is the equation to calculate energy of a photon. What is photon? Photon is a packet of electromagnetic radiation, a packet of energy, that is called photon. So energy of a photon in terms of wavelength. If wavelength is given, how to calculate the energy of the photon? Energy equal to 1240 electron volt nanometer divided by wavelength lambda. Lambda is the wavelength. So for this question, we will calculate the energy 1240 electron volt nanometer divided by wavelength. What is the value of the wavelength in the question? In the question, the wavelength is 515 nanometer. So 515 nanometer. Nanometer and nanometer cancelled from the numerator and denominator. So what is remaining? 1240 divided by 515. 1240 divide 515 equal 2.41 2.41 electron volt. So we got the energy in electron volt. If the question is to calculate energy in joules, how to convert electron volt into joule? Very easy. How? 1.41 times, what is the value of E? You know that E is charge of one electron and its value is 1.602 times 10 to the power negative 19. So equal 2.41 times 1.60 times 10 to the power minus 19 equal 3.85 times 10 to the power minus 19. 3.85 times 10 to the power minus 19 joule. See, 2.41 electron volt, when we convert that into joules, we are getting 10 to the power minus 19 joule, which means this energy 2.41 is a very small energy. If you represent that in joule, 10 to the power minus 19, which means 0. Then about 18 zeros, 0.0000 like that, 385, right? So electron volt is unit of energy to represent very small energy associated with very small subatomic particles like electrons, protons, neutrons, etc. Question number 2 in practice problem. Photon's energy is 2.03 electron volt. What is its wavelength? So here energy of the photon is given in electron volt. We need to calculate the wavelength of the photon. So how to calculate that? We have this equation, energy that is equal to 1240 electron volt nanometer divided by wavelength. We need to calculate wavelength and energy is given, so we will take wavelength to this side. Wavelength is equal to 1240 electron volt nanometer divide. See, when we take wavelength lambda to this side of the equation, it will come like this, right? So this energy will go to the denominator, energy will go here. So 1240 electron volt nanometer divided by energy. What is the energy of the photon? 2.03 electron volt. 2.03 electron volt. Electron volt cancelled. So what is remaining? 1240 divide 2.03. 1240 divide 2.03 equal 611. 611. What is remaining here? Nanometer. So what is the unit? Nanometer. What is wavelength? 611 nanometer is the wavelength of the photon. Question number 3 in practice problems. Rank the following photons from least to greatest energy. First one 4 electron volt, second one 320 nanometer, third one a photon with a wavelength of 811 nanometer, the fourth one a photon with energy 2.1 electron volt. So here the energy is directly given, that is 4 electron volt. Here also energy is given 2.1 electron volt. And what is the energy of this photon? Energy of this photon, if the wavelength is given, energy is 1240 divide by the wavelength 320, right? So 1240 divide 320. 1240 divide 320 equal 3.88. So here the energy is 3.88 electron volt. Nanometer cancelled, so electron volt will be remaining. And in C, 1240 divide 811, that is 1.53 nanometer, sorry, 1.53 electron volt. Its energy is 1.53 electron volt. 1240 divided by 811. So which one is the least energy? The smallest energy. The smallest energy is 1.53 electron volt. Then which one? 2.1 electron volt. 2.1 electron volt. Then 3.88 electron volt. Then which one? 4 electron volt. So this is how we are arranging the photon. Rank the following photons from least to greatest energy. Least to greatest energy. Question number 4. Here a visible spectrum is given. So here will be violet color and red color. So it will be VIBGEO, right? Violet to red. Violet, indigo, blue, green, yellow, orange, red, like this. So a visible spectrum given. The wavelength is starting from for violet 400 nanometer to the red 700 nanometer. The one with the smallest wavelength will have the greatest energy, and one with the longest wavelength will have the smallest energy. So the question is, what is the range of energy associated with? What is the range of the energy associated with visible spectrum? So what is the energy of this red color light? Energy of red color light we can calculate like this: 1240 divided by wavelength 700. How much? 1240 divided by 700 equal 1.77 electron volt. 1.77 electron volt. And what is the energy of the photon with the wavelength of 400 nanometer? 1240 divided by 400, right? You know the equation, right? 3.1 electron volt. 3.10 electron volt. So what is the range of the energy associated with the visible spectrum? 1.77 electron volt to 3.1 electron volt. 1.77 electron volt for which color? For the red color. To 3.1 electron volt for which color? Violet color. So this is the range of the energy associated with visible spectrum. Wavelength is given, you can calculate. If the wavelength is given, how to calculate the energy? 1240 divided by the value of the wavelength, and you will get the answer in electron volt. What is electron volt? Unit of energy associated with very small subatomic particles. EOT question number 2, 3, 4, 5 and 6 are from the topic photoelectric effect. What is photoelectric effect? This is a sheet of metal, and we know that there are electrons in a metal. When light is incidenting onto a metal, electrons are emitted out of the metal, and this is called photoelectric effect. And the emitted electrons, this is called photoelectron. So what is photoelectric effect? When light is incidenting onto the metal, electrons are emitted from the metal. That phenomenon is called photoelectric effect, and the emitted electron is called photoelectron. See, we know that electromagnetic radiation is not continuous, right? It is photon, means it is a stream of particles. Electromagnetic radiation is a stream of small packets of energy, that is called a photon. So we can say when a photon is incidenting onto the metal, the electron is emitted. So this packet, that small packet of energy, that photon will incident and it will eject one electron out of the metal. But there is a condition. That condition is called threshold frequency. Threshold frequency. So what is threshold frequency? It is the minimum frequency the incident photon must have to eject an electron from the surface of the metal. That is called threshold frequency. So threshold frequency is the minimum frequency. If the frequency of the incident photon is equal or greater than that minimum value, then only electron will be emitted out of the metal. And if the frequency of the incident photon is less than threshold frequency, no electrons will be emitted. Why? Because there is another concept, it is called work function. Work function. So what is work function? These electrons are attracted to the metal. The electron cannot simply move out of the metal because these electrons are attracted to the metal. So to move the electron or to remove the electron out of the metal, a minimum energy is required. We need to take the electron out of the metal, so that a minimum energy is required. Why the minimum energy required? Because the electrons are attracted towards the metal. The metal is attracting the electron, and the metal is keeping the electron inside it or on the surface of the metal. So a minimum energy is required to remove the electron or to emit the electron out of the metal. That is called work function. So the incident photon must have a minimum energy to emit an electron out of the metal. That minimum energy is called work function. So what is work function? It is the minimum energy. Minimum energy the incident photon must have to remove an electron out of the metal, and that is different for different material. So work function that I will denote by the letter phi or W for work function. So we know that the energy of a photon, that is equal to h times frequency, right? So threshold frequency, I will write hf0. This is the equation for work function. Work function is the minimum energy. So hf0, what is f0? F0 is the threshold frequency. The minimum means if the incident photon has that minimum frequency, then only it will have that minimum energy to remove the electron out of the metal, because energy of a photon depend only on the frequency. So to have the minimum energy, it must have the minimum frequency. That minimum frequency is called threshold frequency. Suppose this is a sheet of the metal cesium. So this is cesium metal sheet. What is its work function? The work function of cesium is 1.95 electron volt. Okay, let us imagine it is 2 electron volt. Okay, work function of cesium is 2 electron volt. Okay, then this incident photon, the incident photon has an energy that is 1.8 electron volt only. 1.8 electron volt only, and this photon is incidenting onto the metal surface. Can it eject an electron from the metal surface? No. Why? Because the energy of the photon is less than the threshold energy, the minimum energy, the work function required to remove an electron out of the metal. So no electron will be emitted. Okay. Then if the incident photon has an energy 5 electron volt, incident photon has an energy 5 electron volt. So what happens? If it is 5 electron volt, of course that is greater than the work function, greater than the minimum energy, because minimum energy is only 2 electron volt. If the energy of the incident photon is greater than 2 electron volt, of course electrons will be emitted out of the metal. Okay, electron is emitted out of the metal. How much energy is required to remove the electron out of the metal? Only 2 electron volt. So how much is remaining? 5 minus 2. It has 5 electron volt. 2 electron volt is used to move the electron out of the metal. What about the remaining 3 electron volt? The remaining 3 electron volt will appear as the kinetic energy of the electron. It will appear as the kinetic energy of the photoelectron. The emitted electron is called photoelectron. So kinetic energy. Okay. So this one photon can release only one electron. One photon cannot emit 2 electrons. One photon can emit only one electron. For example, if this photon has an energy that is 10 electron volt, then don't think that it can remove 5 electrons. No. One photon can remove only one electron, and the excess energy the incident photon has will become the kinetic energy of the emitted electron. Will become the kinetic energy of the emitted electron. Okay. Then next, if the energy of the incident photon is only 2 electron volt, then what happens? Then it will incident on the metal surface. One electron will be emitted. What about the kinetic energy of the emitted electron? Kinetic energy of the emitted electron will be 0. Why? Because all the 2 electron volt energy the incident photon has is used as the work function. It is used just to remove the electron out of the metal, and there is no energy to give the electron as its kinetic energy. Okay. Then next, another photon is incidenting. So it has another photon. The second photon is incidenting. Okay. The second photon is incidenting, yes, onto this metal, and it also has an energy 5 electron volt, and this electron is emitted. What is the difference? This electron is emitted from inside the metal, and this electron is emitted from the surface of the metal. Which electron will have more kinetic energy? The electron emitted from the surface of the metal, or electron emitted from inside the metal? Of course, electrons emitted from the surface of the metal will have more kinetic energy. So electron emitted from the surface of the metal will have maximum kinetic energy. So what is that is the means maximum kinetic energy will be the kinetic energy of the electron emitted from the surface of the metal. How much is the maximum kinetic energy of this electron? Means how much is the kinetic energy of this electron? That will be 5 minus 5 electron volt minus 2 electron volt. 5 electron volt minus 2 electron volt, that is equal to 3 electron volt. What is this 5 electron volt? 5 electron volt is the energy of the incident photon, that we will write HF, energy of the incident photon. What is this 2 electron volt? 2 electron volt is the work function, the minimum energy required to remove the electron from the surface of the metal. That minimum energy we will write H times threshold frequency, that is equal to 3 electron volt. What is 3 electron volt? The maximum kinetic energy of the emitted electron, Ke max, maximum kinetic energy of the emitted electron. So what is the equation here to calculate the maximum kinetic energy of emitted electron? Maximum kinetic energy, that is equal to HF minus HF0. So H times F minus F0, that is the equation to calculate the maximum kinetic energy. H times frequency of the incident radiation. What is this F? Frequency of the incident photon minus F0, threshold frequency. F0 is the threshold frequency. Now this is a sheet of metal, and suppose the work function of this metal is 4 electron volt, and a photon that is incidenting onto this metal surface. The energy of this incident photon is only 3 electron volt. Will there be any electron emitted? No. Why no? Because the energy of the incident photon is less than the required minimum energy. So no electron is emitted. Now what we are doing, we are increasing the intensity of the incident radiation. We are increasing the intensity. When we increase the intensity of incident radiation, what happens? The number of photons will increase. When we increase the intensity of incident radiation, what happens? There will be more number of photons. Again increase the intensity of incident radiation, again there will be more number of photons. Okay, so increasing the intensity means increasing the number of photons. Intensity is directly proportional to number of photons. Okay, so we are increasing the intensity. Now 3 photons are incidenting. How many electrons will be emitted now? Again 0 electron will be emitted. Why 0? Because none of the electron has minimum energy required to remove an electron. All the incident photon has energy only 3 electron volt. The minimum energy required is 4 electron volt. Do not think that these 3 photons can go together to 1 electron and emit 1 electron. That is not possible. 1 electron can absorb only 1 photon. 1 electron cannot absorb 2 photons energy. Okay, 1 photon can interact only 1 electron. So no electron will be emitted because none of the photon has minimum energy required to remove an electron. Again increase the intensity. Will it make any effect? on the number of emitted electrons? No. Why? Because increasing the intensity will only increase the number of photons, and if none of the photon has minimum energy to remove an electron from the surface of the metal, so no electron will be emitted. Okay, then imagine, suppose the photon has an electron volt, the photon has an energy 6 electron volt. So what happens? One electron will be emitted, and what is the kinetic energy of the emitted electron? 2 electron volt will be the kinetic energy of the emitted electron. Again, increase the intensity. When you increase the intensity, now how many photons are incidenting? Now 3 photons are incidenting. How many electrons will be emitted? 2 more electrons will be emitted. If they are emitted from the surface of the metal, its kinetic energy again will be 2 electron volt, and if they are emitted from inside the metal, not from the surface of the metal but from inside the metal, its kinetic energy will be less than 2 electron volt. This is a glass tube, and here there is a metal. For example, this is a cesium metal, and we are connecting a negative potential here. So this will be negatively charged, and here we are connecting a positive potential, so it will be a positive electrode. So this we call cathode, and the positive potential is called anode. Cathode and anode. Next, the photon is incidenting onto this metal surface, and this photon has energy that is greater than the minimum energy. So electrons will be ejected from this metal surface. Electrons will be ejected. Okay, now electrons are emitted from this metal surface. Now what happens to this electron? Here this is positively charged plate, and this is negatively charged plate. So these electrons are repelled by this negatively charged plate, and the electrons are attracted towards the positively charged plate. So this electron will move to the positively charged plate. The electrons will move towards the anode. So there is movement of electron, and if there is movement of electron, there is electric current. What is electric current? Electric current is the movement of electrons, and we can connect here an ammeter to measure the current. We can connect an ammeter to measure the current. Okay, so we are using the ammeter to measure the current. Here we are measuring the current and plotting a graph. We will plot the current on the y-axis of the graph. And what is the name of this current? This current is called photocurrent. Why? Because this current is due to the movement of the photoelectrons. Why photoelectrons? Because these electrons are emitted by photon is incidenting onto the metal surface. Those emitted electrons are called photoelectrons, and current due to those photoelectrons are called photocurrent. Okay, again we increase the intensity. When we increase the intensity of the incident radiation, more and more electrons will be emitted. When more and more electrons will be emitted, what happens to the current? Current will increase, right? So by increasing the intensity of the incident radiation, here intensity, when we increase the intensity of the incident radiation, the current is increased. Okay, then next, if this incident photon has energy that is less than the threshold energy, that is less than the minimum energy, so no electron will be emitted. If no electron is emitted, there will be no current. Current will be zero. And increase the intensity. Increase the intensity of the incident radiation. Will it make any difference? No. When we increase the intensity of the incident radiation, more and more photons will be incidenting, but none of the photon can remove an electron from the surface of the metal, because they do not have the enough energy required to remove electron from the surface of the metal. Okay, then next let us plot another graph of frequency. Yes. Okay, photon is incidenting onto the surface of the metal. No electron is emitted. Why no electron is emitted? Because the frequency of the incident photon is less than the threshold frequency. Increase the frequency. Now current is 0, right? Current is 0. Increase the frequency. Again no electron is emitted. Why? Because the frequency of the incident photon is less than the threshold frequency. Okay, again we increase the frequency. Now the incident frequency, the frequency of the incident photon become equal to the threshold frequency, so electrons will be emitted. Electrons will be emitted. Okay, the electron is emitted, so there will be current. Then increase the frequency. So what happens when we increase the frequency? The kinetic energy of the emitted electron will increase. When kinetic energy of the emitted electron increases, this electron will move faster. When electron move faster, there will be more current. So after the threshold frequency, until the threshold frequency, current is 0, and after the threshold frequency, when you increase the frequency, current also increases. Why? Because electron is moving faster. Why emitted electron is moving faster? Because this emitted electron now has greater kinetic energy. Now let us do one thing. What we will do here, we will connect negative potential, and this side we will make a positive potential. Here positive potential, here negative potential, like this. So this will be negative and this is positive. Now what happens? Photon is incidenting, electrons are emitted from the metal surface. Then what happens is, now this is negative plate. So this negative plate will repel the incoming electrons. Electrons are moving towards the anode, but the anode is now negative. This plate is now negative, so it will repel the electron. So electrons cannot come. Only the electrons which can overcome that repulsive force, which has more kinetic energy, can move, okay, can reach the anode. So it will reduce the current. It will reduce the current. Now we will make this a variable potential difference, means we can increase this potential difference. So we are increasing the potential difference. Now this plate become more negative. What happens then? It will repel strongly the electron. So for electron it is difficult to reach the anode, because now there is more repulsive force. So electron cannot reach. Only the electrons which has more and more kinetic energy can reach. Again we increase the negative potential here. So again the plate will repel the electron more stronger. So only the electron with the maximum kinetic energy can reach this metal plate, can reach the anode, Then it means which electron will have maximum kinetic energy? The highest kinetic energy, the electron emitted from the surface of the metal, and electron emitted from within the metal cannot reach here. It is already stopped. Okay, again we increase the potential difference to a value until the current is completely zero. Until the current is completely zero means no electron can reach here. The electron with the maximum kinetic energy, the electron which is ejected, which is emitted from the surface of the metal, even those electrons cannot reach this metal plate. That negative potential is called stopping potential. That negative potential can stop the electron with the maximum kinetic energy, can stop the electron that is emitted from the surface of the metal. That is called stopping potential. That is called stopping potential. Stopping potential. So stopping potential that we will represent by V0. Stopping potential we will represent V0. So we can write the maximum kinetic energy of the emitted electron, that is equal to E times V0. What is E? Charge of one electron. E is the charge of an electron, that is 1.60 times 10 to the power minus 19 coulomb, and V0 is the stopping potential. So this is the equation for maximum kinetic energy in terms of stopping potential. Now we will draw a graph of maximum kinetic energy of emitted electron against the frequency of incident radiation. So here Ke max, maximum kinetic energy on the y-axis against the frequency of the incident radiation. So until threshold frequency, no electron is emitted, and at a threshold frequency, the emitted electron will have a kinetic energy equal to 0. If the incident photon has a frequency that is equal to threshold frequency, then kinetic energy of the emitted electron will be 0. Then after that, when we increase the frequency of the incident radiation, the kinetic energy also increases. Kinetic energy also increases. So this is the shape of maximum kinetic energy of emitted electron against the frequency graph. What is the maximum kinetic energy of emitted electron? That is the kinetic energy of the electron emitted from the surface of the metal. So if we calculate the slope of this graph, slope is rise over run, right? Slope is rise over run. So what is rise? Rise is kinetic energy, maximum kinetic energy divide run is frequency f minus f0, right? So what is this? We wrote an equation before. Do you remember that? That equation is h times f minus f0, that is equal to Ke max, that is equal to Ke max. So what is the slope? Ke max divided by f minus f0, that is equal to h, right? See this equation, okay? See this equation, h times f minus f0, that is equal to Ke max, that we have discussed in the beginning of this video, means beginning of this photoelectric effect, not the whole video. And so if I just rewrite this equation, if I take this f minus f0 to the other side of the equation, you know that it will go to the denominator. So if it go to the denominator, Ke max divided by f minus f0, so only h will be remaining here, that is h. See, the slope of the graph is Ke max divided by f minus f0. So slope of this graph is the Planck's constant h. So we can calculate the value of Planck's constant from this by calculating the slope of this graph. Example problem 2. Sodium has threshold wavelength of 526 nanometer. Find work function of sodium in electron volt, and if ultraviolet radiation of wavelength 348 nanometer falls on sodium, will cathode discharge electrons? If so, calculate maximum kinetic energy of the emitted electrons in electron volt. Sodium has a threshold wavelength of 526 nanometer. Find work function of sodium in electron volt. So how to calculate the work function of sodium? Work function, I will write work function, we will denote by the letter phi, that is equal to h times f0, h times f0, that is the equation to calculate the work function. What is h? H is the Planck's constant and f0 is the threshold frequency. And here what is given? wavelength is given. So what is the equation to calculate energy in terms of wavelength? In terms of wavelength, 1240 electron volt nanometer divided by wavelength. So we are calculating the work function. So threshold wavelength equal 1240 electron volt nanometer divided by threshold wavelength. What is the threshold wavelength for sodium? 526 nanometer. 526 nanometer. Nanometer cancelled, and we will get the answer like this: 1240 divide 526 equal 2.36. So the answer is 2.36 electron volt. Then next, if radiation of wavelength 348 nanometer falls on sodium, will there be emission of electrons? Yes. Why? Because see the wavelength of the incident photon. The wavelength of the incident photon is smaller or shorter than the threshold wavelength, which means the incident photon has an energy that is greater than the work function of the metal. So electrons will be emitted. Electrons will be emitted. So for the question B, answer will be yes. Electrons will be emitted. Why electrons are emitted? Because the wavelength of the incident photon is shorter than the wavelength of the threshold wavelength. So if the wavelength of the incident photon is less than the threshold wavelength, electrons will be emitted. Okay. The next, how to calculate the Ke max, the maximum kinetic energy. So first we will calculate the energy of the incident photon. What is the energy of the incident photon? Energy of the incident photon in electron volt, 1240 electron volt nanometer divided by the wavelength, that is equal to 1240 electron volt nanometer divided by what is the wavelength of the incident ultraviolet radiation? The wavelength of the incident UV radiation is 348 nanometer. As usual, nanometer cancelled, and what is remaining? 1240 divide 348 equal 3.56 electron volt. What is 3.56 electron volt? 3.56 electron volt is the energy of the incident photon. What is the value of the work function? 2.36 electron volt, which means out of 3.56 electron volt, the energy of the incident photon, 2.36 electron volt is used just to emit the electron out of the metal, just to remove the electron out of the metal. Why? Because electron is held by the metal. The metal holds its electron in it or on its surface. So to remove the electron out of the metal, some energy is required. That energy is called work function. And if the incident photon has an energy that is greater than the work function, the remaining energy will be given as the kinetic energy of the emitted electrons. Okay, so how to calculate the Ke max, the maximum kinetic energy of the emitted electron, that is equal to energy of the incident photon minus the work function. Energy of the incident photon, here it is 3.56 electron volt minus 2.36 electron volt, that is the work function. So it will be 1.5 minus 3, 2, right? 1.5 1.20 electron volt. So the maximum kinetic energy of the emitted electron here is equal to 1.20 electron volt. Practice problem question number 12. Threshold wavelength of zinc is 310 nanometer. Threshold wavelength for zinc is 310 nanometer. Calculate threshold frequency in hertz and work function for zinc in electron volt, or work function of zinc in electron volt. So how to calculate the threshold frequency? Wavelength is given, frequency that is equal to c by lambda, right? We have the wave equation, c equal to f lambda. So f is equal to c by lambda, and threshold frequency equal to c divided by threshold wavelength. So what is the value of c? C is the speed of electromagnetic wave in vacuum, that is 3 times 10 to the power 8 meter per second. Divide threshold wavelength, this will be meter per second, right? So we will write meter second minus 1. And threshold wavelength, what is the wavelength? 310 nanometer. 310 nanometer. What is nanometer? 10 to the power minus 9 meter. Meter cancelled, so 3 times 10 to the power 8, divide 310 into 10 to the power negative 9. 3 times 10 to the power 8, divide 310 times 10 to the power negative 9 equal 9.68 times 10 to the power 14. 9.68 times 10 to the power 14. What is the unit of frequency? Here what is remaining? Second minus 1. What is second minus 1? Second minus 1 is hertz. What to calculate next? Next we need to calculate the work function of zinc in electron volt. So what is the equation to calculate work function in electron volt? We know the threshold wavelength. Threshold wavelength is given in the question. So 1240 divide the wavelength. Wavelength is how much? 310. So we will get the answer in electron volt. 1240 over 310 equal 4 electron volt. So 4 electron volt is the work function of zinc. 4 electron volt is the work function of zinc. Practice problem question number 13. The work function for cesium metal, that is 1.95 electron volt, and light is incidenting electromagnetic radiation. A violet color light is incidenting onto the cesium plate, cesium metal. What is the wavelength of that photon? What is the wavelength of that visible light, that violet light, electromagnetic radiation? That is 525 nanometer. So electrons will be emitted out of the cesium metal, and we need to calculate the maximum kinetic energy of the emitted electron. Maximum kinetic energy means kinetic energy of the electron emitted from the surface of the metal. So how to calculate the maximum kinetic energy? To calculate the maximum kinetic energy, we have this equation Ke max. Maximum kinetic energy, that is equal to energy of the photon, energy of the incidenting photon minus work function of the metal. Energy of the incidenting photon minus work function of the metal. Here in the question, energy of the incident photon is not given. What is given? The wavelength of the incident photon is given. How much is the wavelength? 425 nanometer. So first we will calculate the energy of the incident photon. Energy of the incident photon in electron volt, 1240 divided by the wavelength lambda, that is 425 nanometer. 1240 divide 425, 1240 divide 425. So the answer is 2.92 electron volt. 2.92 electron volt is the energy of the incident photon. How did we calculate that? Energy of the incident photon, that is equal to 1240 divide the wavelength of the incident photon. How much is the wavelength? 425 nanometer. Okay, then Ke max, right? Ke max equal energy of the incident photon, that is 2.92 minus the work function. Work function is 1.95 equal 2.92 minus 1.95 equal 0.97. 0.97 electron volt is the maximum kinetic energy of the emitted electron. Means kinetic energy of the electron emitted from the surface of the metal. If you have to calculate the maximum kinetic energy in joules, now you calculated in electron volt, how to convert this into joule? Very simple. 1.97 times, instead of E we will write 1.6 times 10 to the power minus 19, and you multiply, you will get the answer. Question number 14, a metal, onto that metal photon is incidenting, and what is the wavelength of the photon? What is the wavelength of the electromagnetic radiation? 193 nanometer. So when 192 nanometer wavelength radiation is incidenting onto the metal and electron is emitted, what is the maximum kinetic energy of the emitted electron? 3.5 electron volt, and we need to calculate what? We need to calculate the work function. So we have this equation. A maximum kinetic energy of the emitted photon, that is equal to energy of the incident photon. Sorry, maximum kinetic energy of the emitted electron, that is equal to energy of the incident photon minus work function. Now you need to calculate the work function. How to calculate work function? We will rewrite this equation. Work function is equal to energy of the incident photon. Work function we will take to this side, so kinetic energy will go to the other side. So minus energy of the incident photon minus kinetic energy. So how to calculate energy of the incident photon? Wavelength is given, so it's very simple. Energy of the incident photon is 1240 divide the wavelength, that is 193, equal 1240 divide 193 equal 6.42. 6.42 is the energy of the incident photon, and work function we need to calculate, right? Work function of the metal. How much is the work function of the metal? How to calculate? Energy of the incident photon minus kinetic energy of the emitted electron. What is the kinetic energy of the emitted electron? 3.5 electron volt. 3.5. So 6.42 minus 3.5. 6.42 minus 3.5 equal 2.92. 2.92 electron volt. So 2.92 electron volt is the work function of that metal. Question number 15. The longest wavelength to eject an electron is 273 nanometer for a given metal. What is the meaning of longest wavelength? Longest wavelength means threshold wavelength. Longest wavelength is the threshold wavelength. So if threshold wavelength is given, how to calculate the work function? We need to calculate the work function. It's very easy. Work function equation in terms of wavelength. If wavelength is given, work function is 1240 divide the threshold wavelength. So 1240 divide 273, and when you calculate this one, you will get the answer in electron volt. Electromagnetic radiation that usually behave as waves can behave as particles also, like small packets of energy, and we call each such packet a photon. Then the particles like electrons, protons, neutrons, etc. can behave as waves also, and we call that waves de Broglie waves. So what is de Broglie waves? De Broglie waves is waves of the particles, waves associated with the particles. So de Broglie waves will have wavelength also, and in question number 7 we will discuss how to calculate de Broglie wavelength. So what is de Broglie wavelength? De Broglie wavelength is the waves of the particles. If electromagnetic radiation that usually behave as waves can behave as particles, then particles like electron, protons, neutrons, etc. can behave as waves also. So when when particle behave as waves, such waves are called de Broglie waves. When particles behave as waves, such waves are called de Broglie waves. How to calculate its wavelength? Very simple. The wavelength of de Broglie wave, we call it de Broglie wavelength, that we can calculate like this: lambda equal to h by p. So in this equation, what is h? H is the Planck's constant. What is its value? 6.626 times 10 to the power minus 34. And what is p? P is momentum. H is Planck's constant, that you know. H is the Planck's constant and P is momentum. What is P? Momentum. What is momentum? Mass into velocity, right? Momentum is mass into velocity of the particle. So we can write de Broglie wavelength lambda, that is equal to h by p. So students, this is the equation to calculate de Broglie wavelength. And what is p? P is momentum. P is momentum, so we can write P is equal to mv. So we can write this equation lambda, that is equal to h by p or h by mv. So what is P? P is m into v, mass into velocity. So we will square both sides of the equation. P square is equal to, if I square the left side, we need to square the right side also. So we can write P square is equal to m square v square. V is the velocity, and I am dividing like this: P square by 2m, that is equal to m square v square divided 2m, because I am dividing left side, so I need to divide the right side of the equation also. So let us cancel this one m from here and one m from here. So we can get P square by 2m, that is equal to, what is this? 1 by 2 is here, mv square. What is half mv square? What is 1 by 2 mv square? 1 by 2 mv square is the kinetic energy equation. So P square by 2m, that is equal to kinetic energy. So we can write P square is equal to 2m into kinetic energy. So what is P? If I take square root on both sides of the equation, P is equal to square root 2m into kinetic energy. And here students, there is one electron, here there is an electron, and you apply a potential difference of V volt here. We are applying a potential difference of V volt, So this electron will be accelerated and electron gains kinetic energy. So what is the kinetic energy of the electron? Kinetic energy of the electron is charge of electron times the potential difference. This is the equation for the kinetic energy of electron. So for electron, proton, like etc., we can write kinetic energy Ke, that is equal to EV, charge of the electron or charge of the proton times the potential difference. So I will rewrite this equation as like this: 2m. For electron and proton, we can write the equation 2m. Instead of kinetic energy, we will write EV. Okay. So these are the equation to calculate the momentum of electron and proton. Okay. So we will rewrite this equation lambda equal to P is square root 2m into kinetic energy, right? So h divided by square root 2m into kinetic energy, so kinetic energy Ke, and lambda equal to h divide square root 2m into EV. So what is this? If momentum of the particle is given, you can calculate the de Broglie wavelength using this equation. If mass and velocity of the particle is given, you can calculate the de Broglie wavelength using this equation. If kinetic energy and mass of the particle is given, you can calculate de Broglie wavelength using this equation. And if the charge of the electron and the potential difference given and mass also given, you can calculate the de Broglie wavelength using the last equation. Example problem 3. An electron is accelerated by a potential difference of 75 volt. What is the de Broglie wavelength? So we need to calculate the de Broglie wavelength. How to calculate that? See what is given, the potential difference given. If the potential difference is given, which equation we will use to calculate the de Broglie wavelength? Lambda equal to h divide square root 2m ev. So we will calculate de Broglie wavelength using that equation, lambda equal to h divide by square root 2m ev. So what is the value of h? 6.626 times 10 to the power minus 34 divide square root 2 times, what is the mass of electron? The mass of electron is 9.1 times 10 to the power minus 31 kilogram times charge of electron 1.6 times 10 to the power minus 19 coulomb times potential difference. Potential difference is 75 volt. Then we will use the calculator. 1.42 times 10 to the power minus 10 meter. So this is the de Broglie wavelength of that particle, de Broglie wavelength of that electron accelerated by a potential difference of 75 volt. Practice problem number 28. What is the de Broglie wavelength and speed of an electron accelerated by a potential difference of 250 volt? So first we will calculate the de Broglie wavelength. De Broglie wavelength lambda, that is equal to h divided by square root 2m ev, because potential difference given. So 6.626 times 10 to the power minus 34 divide square root 2 times 9.1 times 10 to the power minus 31 times 1.6 times 10 to the power minus 19 times the potential difference is 250. 7.77 times 10 to the power minus 11 meter is the value of the de Broglie wavelength of the electron, and we need to calculate the speed, right? The speed of the electron. So we have this equation. Now we know the de Broglie wavelength. So we have this equation, lambda, that is equal to lambda de Broglie wavelength is equal to h by mv. So we can calculate the speed is equal to h divided by m into lambda. H is 6.626 times 10 to the power minus 34 divide m is the mass of the electron. Mass of the electron is 9.1 times 10 to the power minus 31 times lambda is the de Broglie wavelength, that is 7.7 times 10 to the power minus 11 meter. 7.77 times 10 to the power minus 11 equal 9.37 times 10 to the power 6 meter per second. See question number 26 in practice problems. A 7 kilogram bowling ball moving with a speed of 8.5 meter per second, and what is the de Broglie wavelength? De Broglie wavelength lambda, that is equal to h divided by mass into velocity, mass into speed divide. So h is how much? H is 6.626 times 10 to the power minus 34. Mass of the bowling ball 7 kilogram. 7 times speed is 8.5, which equal 1.11 times 10 to the power minus 35 meter. See this answer, 1.11 times 10 to the power minus 35 meter, which means the wavelength of the bowling ball is very small. So the wave behavior of the bowling ball is not noticeable. It is not significant. Why it is not significant? Because its wavelength is very small. Its wavelength is very small. That is why the wave behavior of the particles that we see around us, that we see even in our daily life experiences, that is not significant, not noticeable because of its greater mass. Then where the wave behavior of the particle is significant? In the case of subatomic particles. Why? Because of their very low mass. See this equation, h by mv. See the value of the Planck's constant, 6.626 times 10 to the power minus 34, very small value. So if the mass is not very small like electrons and protons, like subatomic particles, then the wave behavior is not significant, not noticeable. So the wave behavior of subatomic particle is noticeable, is significant. Why? Because of their very low mass, because the mass of electron is 10 to the power minus 31 kilogram. Mass of the proton is 10 to the power minus 26 or 20 minus 27 kilogram. That is why in the case of subatomic particles like electrons and protons and neutrons, the wave behavior is noticeable. The wave behavior is significant. But if the bowling ball, this marker, it has greater mass, right? In such cases, the wave behavior is not significant at all. Question number 27. We need to calculate the potential difference required to accelerate an electron so that it will move with a wavelength of 0.125 nanometers. So wavelength is given and we need to calculate the potential difference. So we can do like this. In wavelength lambda, that is equal to h divided by square root 2 mev, and we will square the equation. So lambda square is equal to h square divided by 2me into potential difference. So potential difference is equal to h square divided by 2me into lambda square equal 6.626 times 10 to the power minus 34 square divide 2 times 9.1 times 10 to the power minus 31 kilogram times 1.6 times 10 to the power minus 34 times the wavelength is 0.125 times 10 to the power minus 9 meter square. So use this in the calculator and you will get the answer. So here I am concluding this video part 1, and after you watch the video, comment. If you like the video, I will make the second part from question number 8, EOT question number 8 to the remaining. Thank you.